Fusion, the international science radio show.
My name's Benjamin Pope. I'm an associate professor of statistical data science at Macquarie University. I work on data analysis and astronomy. I look around other stars. I study stellar physics, and I develop sort of technology for better observing these stars and planets.
All this. So you're working on images from radio astronomy and other forms of astronomy, and you're looking at lots of things.
Radio, yeah.
So amongst the things you've looked at is you've also looked at the nearest star, the sun, and the solar flares and how we can use the history of that.
Yeah, so I mean, I'm very interested in all sorts of problems in astronomy of how can you, infer something about space, right? How can you learn something about stars, planets, the sun, the earth, right? And a lot of the technology that you would use to do that is building big telescopes or exploring, novel sorts of instrumentation to put on telescopes, very clever optical devices or electronic devices to put on them, cameras, spectrographs. But actually, most of what I'm interested in is the other kind of technology that goes on telescopes, that is software. How can we use, basically maths, computer science and statistics applied to our best hardware to tease out interesting signals about space and then learn something really robust about, is there a planet around this star? What's the mass of this star? What's its physics? How are these stellar flares working? How's the sun working, right? And so all of these problems are about, can I write software to look at a whole bunch of messy data, which might be very hard to understand on their own, and then dig something out? Or also, how can I write software to say, okay, what hardware would I need to be able to discover something about the sun or another planet or something like that? How could I design better stuff by using simulations of hardware technology and of stars and planets? And so what this really means is building end-to-end sort of computer simulations of physics and statistical models of how data work and connecting them all the way through to hardware.
Right. So there's a lot to unpack there. So
Yeah. It's a lot of technology.
yeah. So there's a lot going on there. So what is the statistical end? What do you do? Is this to improve how the telescope works, or is this to get information out of the images, or both?
Well, I mean, a bit of both. So, suppose you look at a star with a certain telescope, and you get a measure of its brightness as a function of time, and so it's able to measure it pretty well. You can get it to 1% of 1% precision in its brightness. And so what you want to do is you want to see, is this star vibrating? The sun does. The sun is actually fluctuating in its brightness minutely on a timescale of about 5 minutes. And so the sun is actually ringing like a bell because of all the literal sound. I don't mean this as a metaphor. This is literally sound waves in the sun from the churning motion of the sun's boiling outer layers, right? And so this motion is building up in the sun, this sort of noise, right? And this actually happens in all sorts of stars. Not only that, the sun is magnetic, and through its surface are bursting loops of magnetized material, which sometimes explode. We call that a solar flare, right? And we want to observe this on other stars. And this means that you can sometimes not just see the star sort of ringing, which means it gets a little brighter and a little fainter as a function of time, because of this ringing sort of motion making the outer layers hotter and colder. But also you can see sometimes some flashes. And so far so good. So what you would think is, I point my telescope at this star, and then I see all the flashes and I measure all of the sort of notes at which it rings, and you're done, right? Except it's not so easy. Unfortunately, it turns out that all sorts of other things would cause something to vary in a telescope. Actually, you've got background light from the Earth. You've got planets in our solar system. They're called planets from the Greek for wanderer. It means that they wander across the sky. It means they bloody move. And so what can happen is that you get a planet wanders through the field of view of your telescope when you're taking a long exposure. You can get the phase of the moon, the phase of the Earth as seen from a satellite, all giving you scattered light. And then as your satellite might be going into and out of the sun, you've got, it varies in temperature, which means it expands and contracts, which means its focus moves. So it gets a little in and out of focus, right? On its camera, right? And it's even worse. If you're pointing at one perfect spot on your camera, you can measure the variations in a star pretty well. But actually, if you've got a bit of jitter, if the satellite's not pointing completely perfectly, landing every star on exactly the same pixel every time, well, it turns out pixels on a camera, whether it's this one on your phone or a different one, vary by, maybe a percent between them in how sensitive they are. And
Mm.
so if you're jiggling your phone around, if you're jiggling your telescope around, it's the same thing. Your light keeps landing on different pixels. It's differently sensitive. You can't unambiguously detect a signal. And so statistics, people often think, oh, statistics is when you look at a row of numbers. No, statistics is the science of learning from data, right? That's why, there's no difference at all between the things that I would teach here at Macquarie University in a statistics department and what people are, boldly calling artificial intelligence, except, the scale, the amount of money in it, and the amount of marketing in it. Don't worry, when I put in for grants, I'll call it AI, but this is really just learn from data. You got all sorts of processes that might be affecting your data that are sort of unknown things. How do you model them? There's no equation for them, right? You can't just say, oh, well, I know perfectly how to correct all of this. No, these are sources of error. These are sources of uncertainty. These are sources of mess. And statistics is the science of how do you model those? How do you dig things out of those? How do you properly understand, account for, subtract, or at least, quantify these sources of uncertainty, right? It's just the science of reasoning about uncertainty. And so that's what I do. What it turns out that means is you've got all this sort of quite crappy data from your telescope where you've got all this background light from the Earth and the Moon and the planets, and then you've got the telescopes bloody jiggling around and it's getting hotter and colder. And so the actual raw data that, is the voltages you get out of a bloody camera is rubbish. It's, you can't squint by eye and go, oh, that star's, got a stellar flare. That star's pulsating, or even more excitingly, that star has a little planet passing in front of it, causing a dip in brightness. That's called the transit method. That's how most planets are found. But if you just get a look at the raw data, you can't see any of that. So where statistics comes in is you write software that will take in this data and then will do mathematical approaches to modeling the random effects in it. All of these, sources of scattered light and the different sensitivities of different pixels and all that sort of jazz, right? All, the focus drifts, temperature drifts. And then it will say, accounting for all of these uncertainties, this is how you fit a model to it. And this is the uncertainty that is left in your model fit. Maybe you can't really very accurately back anything out. And then what you want that software to tell you is that the answer is very uncertain. Is there a planet? Is there a flare? Is this star ringing like a bell? The answer is very uncertain. And sometimes that's the way the cookie crumbles. Sometimes you can fix these things, right? And then you can get really, really high quality data by actually fitting some very complicated, software to the data, right? Which says, actually, I'm going to learn the sensitivity of every pixel given the data. There's enough data, you can do that. I'm going to learn a predictive model for how the telescope's focus drifts when temperature changes, because I've got all this temperature data from a thermometer. Well, I can decorrelate, things against that. Well, actually, maybe I've got 1,000 other stars I'm looking at the same time. And actually, they're all being affected by the scattered light and the temperature variations in similar ways in the telescope. The stars should all be different. So if you see them doing the same thing, that's probably because your telescope's doing it. And so all of these things mean that statistics is the fundamental, computer science, statistics, AI, whatever you call it, this is the fundamental endpoint of how you take light from a star and turn it into knowledge about that star, right? And so that's what I work on. What's the maths? What's the computer science of how we can really accurately do this? How can we do it fast? How can we do it precisely and accurately? How can we do it without making serious mistakes, right? And how can we do it in a way that is robust, transparent, and reproducible so that our colleagues at other institutions don't go, oh, Ben says there's a planet there, but there's no reason to agree with him. I think there isn't. No, I have to be able to back it up, right? And so how do you have reproducible science? How do you have science that's defensible, that's clear, unambiguous, or at least where it's ambiguous, you can quantify that. You can talk about it honestly and accurately. That's what statistics is for.
And what has it shown you?
Mm. all sorts of things. And so, one of the papers in my PhD was, simply here is a bunch of really crappy data of stars, right, observed by the Kepler Space Telescope. And Kepler, you don't actually think of Kepler or any other satellite as being a wheeled vehicle, but actually satellites almost universally are, right? Because if you're looking over there and you want to point over there, you could fire your thrusters, to rotate the satellite, except you're in space. Okay, so what happens? You start rotating and you don't stop. You just keep spinning around. And so if you're looking over there and you want to point over there, you actually need to find a way of moving and stopping, right? And so it turns out the easiest way to do that is with gyroscopes. So you have little flywheels inside your satellite, and you've got little motors on them, and you spin one up, and that'll cause the satellite to rotate in the other direction. And then you slow down that gyroscope again, and then the satellite stops, right? And so that's actually how satellites change their orientation, is that they actually are wheeled vehicles, except the wheels are on the inside. And so what's really, really good is Kepler was launched with four wheels, like a car, but actually you really only need a tricycle in space, right? Because you need one wheel per dimension of space. You need up, down, one wheel, left, right, one wheel, front, back, one wheel, right? There's three dimensions of space, or pitch, roll, yaw, if you're actually talking about them accurately as a sort of aerospace engineer, right? And then you've got a spare, because things in space break and you can't easily go up and fix them, right? Kepler satellite's not in low Earth orbit like the Hubble Space Telescope, where you could send a space shuttle up if you still had space shuttles, and have a person get out and get with a screwdriver or something, right? No, like Kepler's a long way away. It's in a really distant orbit, right? And so if something breaks on Kepler, it just breaks. And that's simply, the way it happens. And so when it launched, it had four wheels. After a very short period of time, one of those wheels broke. And so then you go, well, that's fine. You got three wheels left and you only really needed three. It's good that we had a spare. And from then on, though, you're crossing the Nullarbor without a spare is how the satellite's operations are going. You'd better be lucky. You'd better, be very, very careful. And what happened is they actually did very well. I don't know how many of your listeners have been able to go 3.5 years without ever getting a flat tire, but Kepler actually managed to go on three wheels for 3.5 years after its launch, just fine until another one broke. And then you're in trouble, right? Then you have to start firing your thrusters to control that third axis. You can get two of them perfectly stable, but if you want to point at a particular star, and you do, then now you need to be firing your thrusters, maybe just a little bit, right? And so they figured out a really clever strategy. You could fire your thrusters and actually let the pressure of sunlight slow you down. If you just gave it the absolute minimum pulse, right, on that third axis, you could get it kick against the sunlight, and then the sunlight would slow it down and push it back, and then you would kick again, right? It was a completely remarkable feat of engineering that they managed to get this to work at all. But the hardware only gets you so far. What this ended up actually doing, this was about 2014 when I was starting my PhD, what this ended up doing is your Kepler data, and this was one of the most productive telescopes of all time. People think Hubble, people think James Webb. These are star players because they produce beautiful photos, right? But Kepler produced very, very accurate data on brightnesses of stars. So you could look for transiting planets, these planets passing in front, causing a dip in brightness. You could look at stellar pulsations. This is the science of asteroseismology, that is using vibrations in stars to learn about their interiors. And actually, that's how nearly everything that's known about stars has been learned, right? And you can study stellar magnetism. Stars have flares just like the sun. In fact, the sun is very, very low in its magnetism, unlike most stars, which flare like crazy, right? And so these sort of three big things are the main things that you were discovering with Kepler. And they got the thing to keep running. The hardware was fine, but now it's jittering everywhere. Every couple of hours, they fired the thruster again, and your star would streak across a bunch of pixels and then slowly work its way back. And so that meant that you just couldn't see any of these subtle effects in the data. You needed to be able to measure the brightnesses of stars to 100 ppm, 100 parts per million, right? Um, that's pretty difficult. That's 1% of 1%. And you could get maybe data that were 100 times worse just because of this sort of pointing variation. It was sort of just jittering everywhere. Imagine you're trying to take precise measurements out of a shaky camcorder, right? Might look good for a music video, but it's not much good for science. And so what I did my PhD on, and several other people around the world did similar but different approaches to this, was use statistics to try and correct for this effect by learning, machine learning the sensitivities of all these different pixels and the way in which the camera depends on any of the metadata you got, about its pointing or about its temperature or whatever. People took different approaches to this, but the goal was to take really crappy looking data and clean them up and once more be able to detect the variations and brightnesses of stars at this level of precision that would allow us to learn about their physics and the planets that surround them. And so that's what we did. And so it was a really fun project. I worked with my doctoral advisor, Suzanne Grant in Oxford, on doing this, and she sort of invented a method that's now quite widely used. And this is sort of a particular statistical model called a Gaussian process. I won't bore you with the details, but for modeling the brightnesses of stars and correcting for how the telescope might wobble. Sounds boring, but it was vitally important. We were able to discover hundreds of planets doing so. Other people using similar approaches or slightly different approaches based on different kinds of mathematics, but it's all stat stuff that people were doing. Were able to get data of maybe slightly lower quality, but much faster, so they were beating us to publication, or data of higher quality, but it took them longer to do it, and so we were able to beat them to publication, and everything in between. And so it was a very exciting time to be doing this kind of science.
Amazing. And I believe you won a Young Tall Poppies Award.
That was a couple of years ago. So that was when I was back in Queensland. So I was a lecturer at the University of Queensland. And sort of this had been after a period of international travel. So I did my undergrad in Sydney Uni. I grew up in Sydney. And then I did my doctorate in Oxford over in the UK. And then I was a NASA Sagan Fellow at New York University, which is this postdoctoral fellowship that NASA has, where you basically get blank check to do whatever kind of science you think you should. Right? It's very competitive to get those proposals up. And you go, well, how do you stop people just drinking cocktails in New York? And well, to be honest, the answer is you don't. But really, the answer is also they are then under pressure to sing for their supper and get their next job, right? And so you've got 3 years to work on a project. And if it doesn't work, well, they write the money off, but you're not going to get your next job, right? And so it was actually a very stressful time. It's actually much more stressful, I think, than doing a PhD, is doing this postdoctoral research. And for that, I kept working on the Kepler Space Telescope, but I ended up also working on studying sort of stellar flares and these stellar winds and sort of call that space weather, right? The kind of thing that I don't know if any of your listeners were able to see the beautiful aurora from, I guess it was about May this last year, where certainly up in Queensland, I didn't see a thing. But people down in Victoria and particularly Tasmania or New Zealand were certainly able to see very beautiful light shows in the sky. Well, that's space weather. That's the sun reaching out and touching us. That's the sun sending a vast streamer of plasma across interplanetary space that collides with the Earth's magnetosphere and disrupts that magnetosphere, and particles from space flow down onto the Earth's atmosphere and light it up. They cause it to glow. They cause it to fluoresce like a light, like the fluorescent lights above me in this office. I hate fluorescent lights, but that's the same physics, right? And so space weather for Earth is, it's important to geologists. It's important if you're a satellite operator. It can damage power grids, actually, if you get a really big solar flare because it disrupts the Earth's magnetosphere. And so this is a thing that a lot of people in technical disciplines care about. If you've got very sensitive technology or you're worried about very big solar flares and you're managing a power grid, I can get to that later. These sorts of things are important, but there are planets around other stars where They might be in what we call the Goldilocks zone, where they're, far enough from the star not to be boiling like Mercury or Venus, but close enough to the star not to be freezing like Mars. They might have Earth-like temperatures. So far, so good, But the issue is they might, a little bit like Queensland, have a lovely temperature, but be bathed in harsh radiation that makes them hard to live in, right? And so this actually turns out to be a really serious thing that we're thinking about a lot in science at the moment, is that the sun is actually a really quiet star. It doesn't flare very much. Its winds are mild, right? Other stars can be much, much more active in terms of their magnetism, in terms of their winds, in terms of their flares. And we think that to at least some extent, this affects the habitability of the planets around them. That these planets may be facing these very harsh radiation environments where, they're not just worried about getting little aurorae or aren't they very pretty, but actually these events might be stripping the atmosphere of some of its chemicals. They might be even reaching the surface and irradiating things. They might be very difficult environments. And so I started researching that with some of my colleagues in the Netherlands, in particular Joe Callian, who's an Australian academic at the Dutch National Observatory, and some of my colleagues in Sydney. So, for example, Tara Murphy, Laura Dreesen, I don't know, maybe you've even talked to them at the University of Sydney. And so I became very interested in how can observations with Kepler or its successor, a much smaller but more robust ongoing mission called TESS, the Transiting Exoplanet Survey Satellite. How can Kepler or TESS, which basically just measure the brightnesses of stars, also sort of you can combine that information with radio telescopes where these stellar flares give off powerful radio waves. This is actually something that was discovered in Australia by Ruby Payne-Scott, who's a pioneering Australian feminist, Australian astronomer, who invented a lot of the technology surrounding radio astronomy in Dover Heights, just north of Bondi, just after World War II. She was then terribly dismissed from her position at CSIRO because she was a woman, basically. You weren't allowed to be a married woman in the Commonwealth Public Service at the time, and it's really disgraceful. So Ruby Payne-Scott sort of discovered that star spots, stellar flares, or at least she was one of the main discoverers of this. There were other people, Pawsey and Macready, Elizabeth Alexander in New Zealand. But, these people in the 40s discovered that these events occurring on the sun gave off powerful radio waves, and they categorized them into types of radio burst, they called them that had characteristic frequencies and patterns, where you could sort of associate these with where the material on the sun was going, what was happening with it. And so towards the end of my time in New York, I became very interested in working with people like Joe, working with people like Tara, in combining optical data from TESS or from ground-based observatories with these radio data that could then tell us something very interesting about the space weather environments of stars and their planets. And I also became interested again in optical hardware.
Mm.
And my honors and master's projects have been on sort of hardware for doing astronomy, or at least on combined hardware software stuff for doing astronomy, particularly for getting very high resolution images. So not so much worried about, just getting the sensitivity of a telescope to very faint signals, but actually being able to separate them from very bright signals nearby, getting very high resolution, high dynamic range images. And when I say high dynamic range, that's the same thing as when on your phone you go HDR, and then you're able to, see, even though it's a bright sunlit day, you can see faint details. That's was sort of what I was keen on. And it turns out doing that's very hard, and a lot of people have invented a lot of very clever mathematics for taking, for example, in your phone, a burst of images with different exposure times and stitching them together to get a high dynamic range image. Now, in sort of telescopes, it's a bit more complicated because the resolutions you're pushing towards are actually really serious resolutions. And so you need to think seriously, not just about, stacking images carefully, but about the wave nature of light and what the patterns on your camera are telling you about where the light's been and what's sort of been happening to it in the atmosphere, in space, in the sort of guts of your camera, and really picking out, even just a faint speck of dust or a little warp on a mirror or a lens can completely kill you. And so how can you accurately infer stuff given that? And so, yeah, I guess that's a roundabout way of saying it was very nice when the Queensland government, the sort of tall poppy organisers, gave me that award. But what it represents is a lot of collaboration with a lot of people, particularly people like my DPhil supervisor Suzanne in Oxford, or my colleagues like Joe in the Netherlands, or David Hogg in New York, who sort of I was working with and learning with to try and figure out new ways to apply stats, applied maths, computer science to trying to find these faint and difficult signals. And so I was very pleased. Got to meet the science minister, got to shake a hand, and yeah, it was good.
Sounds amazing.
Where were we?
Way back. And you were going to tell me about the thing that's most on your mind at the moment.
So the thing that I've been working with a group of PhD students here and postdoc in all over Sydney and Brisbane, it's the wonder of modern remote work is you've got a great network of people internationally as well, people in Baltimore, people in Montreal, people in Vancouver. Um, we're working on an instrument, uh, which, a camera on board the James Webb Space Telescope. So the world's biggest, most expensive ever space telescope, right? James Webb is transformative. The last time there was such a significant investment in astronomy was when the Hubble Space Telescope launched 4 months before I was born, right? So, you can go your whole lifetime and become a university academic in between drinks, working on large telescopes. These are, it's in some senses, these projects are like cathedrals. They're built by more than one generation, and they're used for more than one generation. They are massive undertakings. So James Webb, look, really remarkable. Let me not talk it down, but there is a problem with it. At its very highest resolutions, James Webb is slightly blurrier than it should be. This is actually not a problem in the manufacturing of James Webb or something like that. This is actually common because James Webb is an infrared instrument, so it looks at wavelengths of light all the way from the very red wavelengths that humans can perceive, all the way through to thermal infrared that you might be, having night vision goggles to go on a safari, or heaven forbid in the military, that sort of thermal infrared. Because infrared light is able to look through dust. It's able to see warm stuff, but also peer through obscuring stuff. That's why it's so useful in the military. That's why it's so useful to astronomers. And so these infrared cameras are actually all slightly blurry. It's a fundamental issue to do with how they work. In the detectors, they have something called a brighter, fatter effect. That is, a brighter pixel bleeds a little bit of signal into its neighbors, so that a little bright source gets fatter the brighter it is on your camera. That's all. I mean, very high technical science, right? Like that's as technical as we go in terms of words, right? So this BFE, as you might call it, is really seriously limiting the capacity of James Webb to get high resolution images, not high sensitivity. It's got these beautifully deep exposures of space, revealing all sorts of wonderful things. But if you're looking for a little dot next to a very bright dot, this BFE kills you. Because what happens is that bright dot bleeds all over your little dot, and you can't see a planet around a star. So, except in a few cases where it's a planet that's unusually bright and far from its star, James Webb hasn't been able to do what we'd hoped, which is to directly image planets around stars, even though it's been able to do many other things that it was hoped to do, such as to measure the spectra of planets and stars and galaxies and everything like that. So we have this little piece of hardware. I know you're recording video as well as audio.
Yes, yes.
Yeah, it's good. So we've got this piece of hardware. It's called the aperture masking interferometer, right? Which was developed in Australia by my big mentor, Peter Tuthill at the University of Sydney, in order to get a really, really precise calibration of the optics and detector of James Webb, right?
The
And
disc.
so, yeah, this is just a little disc of metal. I'm just holding it up. Can you see?
Yeah.
Perforated holes. So if people are on audio, they won't be able to see, but basically there's 7 little holes in a disc of metal that you place in the path of the light. And the holes filter the light so that only the light passing through those holes gets through, right? and forms a distinctive pattern on the detector. Now, these holes are designed with a certain mathematical precision so that no two holes are separated by the same direction and distance. And it turns out that this is a mathematical requirement for being able to unambiguously determine what the pattern of light on the camera corresponds to in terms of things that have disturbed the light, say misaligned mirrors in the telescope, stuff like that, right? And so what it means is we can project a perfect test pattern onto the detector. And even if it's not the test pattern that we expected, because some mirror is misaligned, we can know exactly which mirror is misaligned where, right? And so we can learn it perfectly, or at least as close to perfectly as you can reasonably expect. Um, and so this has been really, really important because now we can go, okay, well, you've got a blurry image. Well, we know what pattern it should have. Then we can try and machine learn. So it's all statistics, it's all AI, it's machine learning, it's the same stuff. It's a neural network. It's the same stuff as powers ChatGPT or Stable Diffusion or whatever people are using to plagiarize. It's the same sort of thing, same mathematics to go, okay, we have this known test pattern on your camera. Now we've got the, fuck me,
What happened?
emergency. Got an evacuation. Sorry.
Oh no. All right. Are you well, be safe. Thank you for your time.
Give me 10 minutes. Sorry, mate.
Okay. All right. Do you want me to log out and yeah. Wow. Hi.
Sorry, we got evacuated. Just got let back in.
Was it
It's
just a test?
It wasn't a test. They didn't tell us what it was. Look, I'm sure someone just put a test or something. You know how these things are. But fire brigade didn't come, but we were just sort of milling outside for a while. I actually bought a coffee. Anyway, I apologize for that. I think we were up to something in the middle of talking about James Webb's AMI.
I think so, yes.
Yeah. I've no recollection of what the last thing I said was, but basically, I'm really excited about this is Australian hardware on James Webb.
Yeah.
You know, entire instruments, large instruments have been built by, say, the Canadians or the Europeans. And I think it's really disappointing that Australia has had such a small contribution to space-based astronomy until very recently. We've only just recently launched our first space telescope, a Spirit from University of Melbourne, hoping to launch another one led by Peter Tuthill from University of Sydney called Ptolemy.
Mm-hmm.
This is hardware on James Webb, and I'm very proud to be involved in the team using it. And yeah, so we've been building software using very modern machine learning methods to you look at a star and then you have to learn a model of how the electronics behave and how the optics behave to be able to figure out sort of which bits are misaligned, which bits in the electronics are performing poorly with this brighter, fatter effect. And I'm very, very happy to say that this model is actually accurate enough to significantly improve the resolution and sensitivity that we get. And so that's really cool. I mean, this is not something we've published yet. This is one of the perennial struggles of doing science is publishing and managing the timelines of student projects. So this is work mainly led by, the instrument was designed by Peter Tuthill, as a professor at the University of Sydney. But the project has been a project Peter and I have been supervising by a couple of PhD students, most notably Louis Desdois, who's a PhD student at the University of Sydney, building this machine learning model of the whole James Webb sort of camera leading up to this thing. And very happily, he's now got a job in Europe. But sort of how do we manage the timelines of all of these projects? This is the perennial struggle of science. So it's something that's consuming a lot of my thoughts at the moment as we try and get as much data from James Webb as possible, analyze it in such a way as we can refine all the parameters of this very, very big and complicated model in order to be able to enhance the resolution, ideally to correct in post this brighter, fatter effect. It's a bit like, how in detective dramas, they might get a blurry photo of a criminal, and then they'll go computer enhance, right? And they'll get a really high resolution photo. Now, one of the very common things that you'll hear science communicators, science nerds, science fans talk about is, well, you can't do that. Obviously, you can't do that. You've only got 4 pixels. How can you deblur to get a really, really high resolution photo when you've only got so much information? Obviously, these shows are getting it wrong. It's not true. It's not real. This is creative license if you're positive, or it's science illiteracy if you're negative about it. I see posts like this all the time on social media. I hear people say this. Well, the funny thing is that's not true. You
Mm.
absolutely can go computer enhance and deblur a photo.
Mm.
And the trick is that you might only have a very small number of pixels, but you do have some sense of what's behind those pixels. That is, if you're looking at a face, it's going to look like a human face, right? And so you now can go, well, a human face isn't a very high dimensional object, right? There are only so many parameters that you would need to describe a human's face. I don't know if you've played, one of those computer games where you can, adjust all the sliders to control the face of your character in Dragon Age or whatever, you know. But actually, you don't need many sliders, and you can change the face a lot, right? So actually, if you've got a model of that, you might have, I don't know, 10 pixels on a face, but there might only be 10 relevant variables that matter, right? You might have what color's the hair, right? What color's the skin? Is it a wide or a narrow face? How big's the nose? How big's the mouth? Well, actually, once you've specified those, you're pretty close to describing what a person looks like, right? And so actually you totally can do deblurring of an image if you've got enough what we call prior information. That is, before you even looked at the data, you knew roughly what you were going to see. It was going to be a human face, or it might have been a number plate. This actually technology was originally invented for deblurring number plates of speeding motorists, right? Then what you can do is you can do what's called a deconvolution, is what the mathematical operation's called, a deblurring, where you know something about the object that you're looking at, and you also know something about the process that is blurring the image. And in fact, these two kinds of knowledge are perfectly symmetric, because if you blur one image with another image, it's the same thing as if you did it in the other way. It's like a multiplication, right? And so any amount of information that you can get about, what's the blurring kernel, they call it, what's the pattern with which you're blurring the image, or about what kind of image you're likely to see, will enable you to do better and better at this task of deconvolution, computer enhance, and you get the image of the number plate of the speeding motorist, or you get the mug shot of the perp, right? Or in our case, you get an image of what the star and the planets around it might have looked like, where what we really don't know enough about astronomical scenes to do this, and really there's not a lot of richness in the information there. They're just sort of dots, right? But we can learn a lot about the blurring process, the optics, the electronics, all of that, and that can help us deconvolve. And so, yeah, so building this sort of very large data-driven model of how James Webb works allows us to, computer enhance the photos, get higher resolution, but it's not faking it, right? It's not just inpainting spurious detail. It's getting real detail out that's in there because you know the process that corrupted it, right? So that's what we're all about.
So that's where the test pattern comes in that you had
Exactly.
with the
Because we've got this, yeah, that's what I was talking about before we got interrupted with the fire alarm. Because we got this aperture mask in there,
Yep.
this structures the light. So at least the optical component of this blurring, the electronics are a different thing, but at least the optical component of the blurring is very precisely known, right? Or at least it's precisely inferable, because any pattern of light on the detector uniquely corresponds to a single configuration of mirrors because of the mathematical properties of this mask. It's quite clever. Well done, Peter, for sort of inventing it. And then because you know the optical pattern, and maybe you're looking at a reference star that you know to be a dot. For example, we pick what are called K giants, which are what something like the sun will be when it dies and evolves off the main sequence, because we know that they're very, very bright and far away, and they enormously outshine anything that's around them. K giants are reliably dots. And so we're just looking at this thing and we know it's a dot. We know reasonably accurately what wavelength of light it's emitting, right? And so then we can say, well, it's a dot and it's been blurred by the optics and something else, these electronics. And so then we build a neural network that learns what the electronics are doing. Boom. Now you've got a model of the whole thing, and you can go look at, a system of, a black hole with stuff around it, orbiting around it. Well, we that's one of the projects that one of the students, Max Charles, great student at University of Sydney, is working on, is de-blurring these images of a black hole taken with James Webb, and hopefully we'll publish those very soon. Other students that we're working with, there's a group in Vancouver, or rather Victoria, Canada, Victoria, British Columbia, just across the sea from Vancouver. Doug Johnston and Dory Blakely, they're looking for newborn planets being born out of disks of gas and dust, just like the Earth was 4.5 billion years ago. We're not able to get baby photos of the Earth because that was too long ago and there was no one to take a photo, but we can get baby photos of other planets being born just in the same process as the Earth or Jupiter or the other planets in our solar system were, and sort of learn about the physics, the fundamental sort of reasons why planets are born in the way that they're born. The emerging sort of science is that there's probably things called dust traps. That is, swirls of gas that trap and concentrate dust in such a way as to accelerate the process of planet formation. That's one thing that people have been finding over the last few years. And so looking for evidence of these sorts of theories in these high resolution images of the dust around, young stars is a very important thing to be doing.
And so how do you apply the convolution to those sort of images? Do you know what you're looking at?
You take a picture and it comes out looking like a pizza. It's blurry all over, and it's even worse because it's been blurred by the weird optical pattern of this, as well as by the electronics. And then you run it through your software that can then reassign where all the light should be correctly to get a high resolution photo. And you have to benchmark the hell out of that by looking at reference stars to make sure you're really getting it right. Yeah, I mean, that's what you're doing. You're taking a photo with a camera on James Webb with this sort of component in it, and then you are correcting that photo. It's not Photoshop where you're like, oh, I'm gonna draw a smiley face in it. That's not what we're doing. We're mathematically saying what possible configuration of astronomical stuff could be causing this image, given what we know about the detector and given what we know about the optics, because we are really pushing the limits of how does the detector perform at the 1 pixel level, and how does light, interact at the 1 wavelength level. That's where we're up to, getting nanometers of precision on the optics, right? And, a few counts of electrons precision on the detectors. That's where we're at. It's very fun work. I'm sure Louis would disagree that it's fun right at this end of his PhD because he has to submit in a couple of months.
Yes.
But I think it's fun as his supervisor, and I think it's fun as someone who's worked on this project ever since actually my honors was on sort of a much less sophisticated approach to doing the same thing to Hubble Space Telescope images.
One moment. I just need to tell someone to stop calling.
That's right.
There we go. It wasn't quite working. Sorry about that.
Yeah.
It does sound absolutely amazing that you can get those sort of images and that you can see planets being born.
Sorry, I was just responding to a message myself while you were checking your phone. Yeah.
Sorry.
Sorry, I've got many appointments today, and
do you need to wrap things up? Are you
probably
running
in due
out of time?
with no great urgency.
All right.
The thing I had to do at 3 is probably not going to happen. Anyway, yeah, look, watching planets being born is great. It's a great privilege. You get to see a fundamental process, which is sort of one of the, 50 years ago, you simply didn't know anything about this process really. And now we can quite accurately sort of talk about the quantitative detail of how this happens. And this is one of the sort of steps towards understanding how did Earth form, is how did planets in general form, and how did life form? In particular, how did Earth get oceans? How did Earth get a nice atmosphere like the one we have? instead of a hellish atmosphere like Venus, or lose its atmosphere like Mars, right? So all of these things, taking these images, taking these spectra of other planets very early in their lives, help us understand what Earth and Jupiter and Mars and Venus were doing early in their lives by looking at analogies in other systems, and then mathematically model their behavior in order to understand, where did Venus go wrong? Where did Mars go wrong? Why is Jupiter as big as it is? It's pretty big. It's actually not nearly as big as gas giants sometimes go, but we think that may be the most massive gas giants formed by a different process. So this is the sort of thing that we're trying to understand.
Wow, there's a lot there. So you're able to use this to improve the images and get data about all the objects that you'd be looking at in the sky.
Very much once you've got a new technology, right? Charlie Towns described the laser as a solution looking for a problem, right? New technologies. I also like to think about Leonard Cohen. He's got this line in First We Take Manhattan. I'm guided by the beauty of our weapons, right? Once you invent something cool like this, you can apply it to all sorts of problems. So people use some of the sort of same mathematics from astronomy for image deconvolution, actually is how MRI was invented. And Ron Bracewell, an Australian sort of pioneer of radio interferometry, radio astronomy, how do you get good images out of radio data, was one of the pioneers of actually, turning astronomy into medicine by doing this for MRI imaging, right? And
Hmm.
so of technology in general is very widely applicable, not just across astronomy, but across science in general. And that's sort of at a high level. I'm just about to go to Canberra and talk to Parliament about why they should support science. This is sort of one of my pitches, right? Is you don't know where technology will lead you, right? You don't know what outcomes things are going to have. Politicians always love to say, I'd love more applied science, but all applied science was a pure science once, right? When you are pushing the limits of maths, physics, chemistry, computer science, whatever it is, it may look like, oh, well, these people are airy-fairy scientists working on sort of head in the clouds things. But what we're doing is we're finding, okay, here is a particularly interesting or difficult problem which we're close to solving. And we're going to solve the ones that we can get our hands on with the technology that we have, and we're going to then learn from those. And then maybe we transfer those to other problems. And so there's no real distinction between pure and applied science, in my view. There's science that is being applied right now and science that hasn't been applied yet. But I think even very obscure branches of algebraic geometry, one of my best friends is an algebraic geometer, which is a particularly obscure kind of mathematics about studying the shapes that polynomials form, squares and cubes and so forth, and ellipses, but in much higher dimensions and much greater sophistication. And one of the things he likes is how arcane and removed from ordinary applications it is. At least that's what we all thought, 10, 15 years ago. Well, it's not merely got applications in theoretical physics, but actually underpins a lot of the machine learning we're doing now. A lot of those mathematics actually tell you about the behavior of neural networks. So, even things that are very, very pure actually turn out to actually touch on a lot of things. Science is fundamentally interconnected, that you can't easily separate, as you can in a classroom, physics from chemistry, from, mathematics from biology, from whatever. These things all bleed into each other in a very complicated way. And so that's why, for example, I'm quite excited to be working in a statistics department in Macquarie, where I've often worked on statistics things before, but actually my primary affiliation's been physics. Well, it may seem, well, those are completely different things. If you're studying an undergraduate curriculum or a high school, those are different subjects. You go to different classrooms for that. Yeah, actually, if you're a practitioner, you have to know a little bit of everything, and in fact, a lot of everything, to be able to make progress in any one of these disciplines. And if you sort of accurately talk about what an individual scientist does in their career, they're actually probably touching on things taught in many different classrooms in many different contexts. Yeah.
There's so much there. So, um, is there anything you'd like to talk about that I haven't asked you? Because I don't know how much time you've got left.
I don't really have that much time. I would have loved to have talked about radiocarbon and tree rings and so forth, but I'm afraid I actually have to
Well,
run off.
maybe another month.
But another time.
Yes, for
Uh,
sure.
well,
Well,
look, it's been a pleasure to meet you, Ian. Is there anything you wanted to talk about before I run off?
um, I think, well, look, you've covered a lot of really interesting subjects there. So, the only last thing I would have put is people, if there's students listening that would like to follow in your footsteps, what subject should they look for at university?
At university, study the things that you like and enjoy the most. Don't let anyone tell you what to do because it'll lead to a good job, because the job market is so chaotic now. Even things like law or medicine, there are crises where people are, having their jobs disrupted by terrible governments pulling funding through to new technologies being invented that, ruin whole subdisciplines, right? The kind of thing that you should do at university is the thing that you enjoy. And that doesn't have to be science. The subject I enjoyed most at university was Old Norse. I studied Old Icelandic literature, loved it. You know, but if you want to get a career in science, you can't do it simply by doing just one thing initially. You want to get a broad base of, physics, maths, computer science, chemistry or biology if you're really into those. You don't really need much biology if you wanted to go into, natural science, but if you want to go into anything biomedical, you need to. But in natural science, you need to touch physics, chemistry, maths, computer science, statistics, all of that, because you don't know yet where it's going to go. And if you think, oh, I want to be an astronomer, that's great. I think astronomy is great. If you think I want to be a paleontologist, if you think I want to be any one of those things, and I'm going to dedicate my whole undergraduate to singularly pursuing this goal, in my experience, that's a mistake. People who do this end up in things where actually they don't really like the workflow of the day-to-day activity of that thing. Actually, it would have been better if they'd, just followed their experiences and enjoyments and curiosities at undergrad as much as possible. And then they find the thing that suits them the best. They find the people that they like to get along with in the culture that they enjoy. And that's really great.
Fantastic. Well, Benjamin Pope, thank you very much.
Thank you very much. Look, good to talk to you.
Study science, because you will find in the study of science a richer, more rewarding life.